Last time we looked at the core tasks for cryptography. Now, in essence, cryptography is used for two things. First, secure communication, and second, partly to achieve secure communications, secret key establishment between two parties. Key establishment is crucial in order to talk to someone on the internet. This someone could be another person or a service or a server somewhere. It is vital for two parties, let's call them Alice and Bob, to be able to agree on a shared key or a secret or a passcode, let's call it K in this instance, in order to secure all of the communications, as in using that shared secret to encrypt communications between them. It's only after this key establishment has been made that two parties can communicate securely so that confidentiality and integrity remains intact in the messaging. It's also important to remember that cryptography can do much more than that. That is its day-to-day job, but cryptography will also be able to provide you with things like digital signatures. Digital signatures can be used to identify someone online. The flip side of the coin is that cryptography can also enable completely anonymous communication, so that if identification is not even desired, it would be possible to communicate completely anonymously. Another application area could be digital currencies. You may have heard of cryptocurrencies such as Bitcoin, Litecoin, or Dogecoin. Depending on the particular cryptocurrency, these currencies are more or less traceable online. The actual problem that cryptocurrencies solve is related to the questions of how can I spend a digital coin without anyone knowing who I am? And also, if it's possible to do cash transactions anonymously, how would you prevent double spending? After all, if you had one digital coin which is stored in a file on a computer somewhere, what prevents you from simply making a copy out of it and using it again and again? The clever trick that cryptocurrencies employ to actually achieve this is actually rather simple. Usually you can spend as much digital cash as you want, and as long as you don't go over the limits of your account, no one will be able to trace it back to you. If you start double spending your money, then your anonymity is compromised. So that's the clever way how cryptocurrencies usually solve these two problems. The third important application area for cryptography is to implement different types of protocols. As an example of a protocol, let's look at a protocol of an election. In an election, our target is to compute a winner amongst different candidates. Let's say there are two candidates and we mark them binary with a 1 and a 0. So 1 is for candidate number 1. Candidate number 1 here. And 0 is for candidate number 2. Here we are. Usually how elections go is that there is an election center somewhere which is tasked with collecting and tallying up the singular votes from different people, and they are also tasked with the problem of checking if this person is eligible for voting in the first place. And after that process is completed, the election center can proceed with the tallying of the votes to figure out who is the winner of the election. So the goal in an election is simply to compute who wins the most votes. So it's some sort of a function that depends on all of the individual inputs from the people who are eligible to vote. The cool thing that cryptography allows us to do is to get rid of this election center. So what cryptographic applications allow us to do is basically for the voters to calculate the outcome of this election without having to share their votes with a trusted third party. There's actually a lemma in cryptography that states that anything that can be done with a trusted authority can also be done without one. This kind of a process is more formally known as secure multi-party computation. Then there are some cryptographic applications which can only be appropriately described as magic. For instance, outsourcing computation securely means that it's possible for us to encrypt data or encrypt our files and send them off to be processed so that even the processor does not know what is the data that they are processing. So for instance, you could make a secure Google search where you can see what you are typing into the search prompt. It's then encrypted and sent encrypted to Google to do this Google search, but even Google cannot actually find out what it is that you searched for. So in this case, the service provider Google would actually complete this search using only encrypted data, and they would never have any idea of what were the actual search terms. The other interesting way to do secure computation is what are known as zero knowledge proofs or zero proof of knowledge proofs. Zero knowledge proofs are a way of showing that you know the solution to some particular problem without actually saying what it is. What you can do is use mathematics to show that you know the solution to pretty much any puzzle. It could be a game or a Sudoku, whatever, and prove that you do have the solution, but you don't actually have to show that solution to anyone. And we, the bystanders, will be completely convinced that you in fact know the solution to that problem. Because zero knowledge proofs can be a little daunting to look at first, let's take a practical example using something that we could relate to. So let's say one day when walking to class you find a phone on the hallway and you walk into the classroom and ask, does anyone know who it belongs to? And then someone says, oh, it's mine, I lost it earlier, thank you very much for returning it. Now usually people of course are honest, and you probably will be able to find the true owner of this phone. But let's think about this. Is there a way of figuring out who the owner is in a secure way? So it turns out that this is a perfect example of what a zero knowledge proof can do. Most mobile phones are password protected. So what the owner of the phone can do is that they can show that they know the passcode by simply unlocking the phone in front of you. And the zero knowledge part of this proof comes from the fact that you can hand the phone over to someone, they can unlock the phone and show you the unlocked screen without actually having to tell you the passcode. So the data that this person knows is their private passcode, and in order to prove that they actually do know the passcode and probably own the phone as well, they can simply use their knowledge and you will be none the wiser about the contents of the passcode or the phone.